Thank you very much. So today I'm going to talk about how we are enabling the sensing and mobile health communities, including researchers, doctors, patients, caregivers, with a completely open platform for wearables and mobile health research. So we call this the Amulet Platform. So we're seeing serious interest in all manner of wearables in a lot of different applications. We've seen a few already today. In the consumer side of things, we're seeing wrist-worn wearables in the market that fall broadly under two categories. Let's just call them wristbands and smartwatches. So wristbands, like the Fitbit, are usually longer lived, but they have limited or closed applications from a single provider. So smartwatches, like the Apple Watch or Android Watch, have much shorter lifetimes, but provide stronger security properties that allow multiple applications from different developers to coexist peacefully on the same device. So both of these types of devices have closed hardware, maybe even a closed operating system. Both of these types of devices and their platforms rarely help the developer make better choices in code to make their apps last longer for the benefit of the user. So my question is, why do we have to choose between flexibility and energy consumption? Why do we require our users to plug their device in every night? And why do we force developers to make assumptions about how their application affects the device's lifetime? So if we think of other applications for these devices beyond basic consumer interests, we find that these questions make it tough to conduct research in the medical fields, where patients can often have disabilities or impairments that prevent them from managing their device. So we find it difficult in the sensing communities to help mobile health researchers make interesting explorations because we are constrained to these closed commercial platforms. So for these reasons and others, we think that the sensing and mobile health communities need an enabling platform to simplify wearables research and mobile health studies. So we think our platform, Amulet, can fill this technology gap. So in this talk, I'll first give an overview of our design considerations for Amulet. I'll talk about the Amulet platform and the different pieces involved. I'll give some results from our evaluation and user studies, and I'll close with some interesting avenues for future research, as well as some details about how people in this room can start using Amulet in their own research. So let's talk about design considerations. So what does Amulet need to look like? What are the goals? So here are the key requirements we identified from our own experience, talking to medical professionals, talking to usability collaborators, and talking to the actual developers. So the first kind of consideration is that this platform needs to support multiple applications. Users don't want to wear multiple single-purpose devices, all with their own unique ecosystem that can't coordinate with each other. So the platform has to be able to support multiple developers writing distinct apps with distinct functions. This means that the platform must support a way to isolate applications' data and code from each other. So traditionally, in higher-powered devices like the Apple Watch and the Android phone, this is done using a dedicated memory management unit, which is not available in our low-power processors. So the second design consideration is the need for long lifetime. So battery life is a critical feature for mobile and wearable devices, rated by far the most important feature by users of today's smartphones and wearable gadgets, according to a lot of studies. So when you have lifetime measured in weeks, in months, in years, long-term studies of smoking cessation, for example, become possible. This also decreases the chance for devices to be lost, stolen, or broken, as the user will not have to take the device off their wrist. So the third consideration is the need to enable developers to understand where their energy is going in their application. So right now, the best guidance developers get are a few documents talking about best practices and tools that profile energy usage in the wild after the app is already mostly written. So these tools can't provide real-time, compile-time, in-the-moment information about how changing a line of code or the timing of an event will change the total app current draw over the entire device lifetime. So if devices are going to be made that claim long battery life, the platform must support the developers to help them actually accomplish this. So finally, this platform has to be completely open. I realize that some of the choices we made when designing the Amulet platform might not be appreciated by everyone. Other people will want to augment or improve Amulet functionality, maybe add operating system or hardware support for their own sensors, for their own applications, their own design flow. So by keeping the entire platform open, including the hardware, the operating system, and the tools, we enable researchers to improve on existing systems without having to design everything from scratch. So with these considerations in mind, we designed the Amulet platform. Amulet is made up of 4 distinct parts: the low-power, open hardware watch form factor, the Amulet OS, serving as the main interface between the device and the programmer, the Amulet firmware toolchain, which constructs multi-application firmware images that can be installed on the device, and the Amulet resource profiler and interface, which profiles and predicts the energy usage of each application in real time and provides a simple interface for the developer to explore how their code affects the battery lifetime of the device. So let's look at each of these parts individually. So this is our most recent Amulet prototype. So it's centered around an FRAM-enabled MSP430 processor, along with motion and environmental sensors, a Bluetooth low-energy radio for communication in master and peripheral mode, and a custom-designed 3D case that encloses a buzzer, a micro SD card reader, and a battery. So the Amulet has multiple interactive elements. We have 2 flexible buttons, a low-power LCD display, and a capacitive touch slider for touch input. Right now it comes in black, white, Clemson, burnt orange, and Dartmouth forest green, and maybe some glow-in-the-dark if anyone wants that, besides me. The prototype is designed for low-power operation, drawing around 20 microamps while maintaining a display, reading the accelerometer at low frequency, and responding to user interface events. So higher power components like the gyro, the SD card, and the Bluetooth chip can be completely turned off to conserve power and only turned on when needed by the application itself. So this first prototype is a watch form factor wearable, but we anticipate future wearables in different form factors and on different parts of the body. So continuing, the Amulet OS is the interface between the programmer and the device itself. So we want it to be easy and straightforward to develop long-lived, sophisticated, useful applications, even for novice programmers. So developers design the apps by specifying a state machine. States are linked by events that can be specified by the user, are originated by the environment, or are originated by the operating system itself. These events are consumed by handlers, which are non-blocking functions written in embedded C that may consume data arriving with the event or update app variables, call Amulet APIs, or send new events in any combination. So developers construct these state machines using the event-driven QM framework and interface. So by having developers encapsulate their functionality in a state machine, the operating system and tools can help the dev make a decision about the impact of code blocks on energy. So this structure helps the platform duty cycle more efficiently by running handlers to completion and not maintaining any thread state or other overhead. So we also provide an API that allows developers to control sensing, storage, signal processing, communication, timing, and user interactions. This abstraction allows developers to focus on the application instead of getting lost in driver hell. So we also provide a way for applications to subscribe to sensors so that multiple apps can share a single data stream. So when you think of Amulet OS, we call it an operating system, but it's really more of a lightweight runtime system. But it still supports a rich set of developer actions and multiple applications on a constrained system without hardware memory management. So how do we actually protect memory and keep applications isolated from each other. So runtime methods are too expensive. We don't have hardware support, so we protect at compile time. So the Amulet firmware toolchain, or AFT, manages the analysis, the translation, and the compilation of the final firmware. So there's really two parts of the AFT: the application isolation mechanism that makes sure multiple applications can live in harmony on a single unprotected memory device. And then the second mechanism is the resource profiling, which is used to support developers in real-time optimization of the battery lifetime for a specific application. So let's look at how this works at a high level. So since we don't have memory management inside the MSP430 and we don't want to waste cycles doing memory checking and software at runtime, we have to ensure application isolation before the apps are loaded on the device. So we constrain some of the things developers can do to ensure everyone plays nice while they're on the same device. So we require a few changes to C that allow us to make assumptions about app state and to ensure that apps are isolated from each other. So developers can't have dynamic memory allocation, they can't use pointers, and we make sure that arrays have explicit links at compile time. So once the developer has partially or fully written their app, the first step to a complete firmware from the AFT is to analyze the developer code, ensuring it doesn't violate any of these rules, and then continue on. So after this analysis, the AFT looks at resource usage, specifically energy usage, building a parameterized model of the application's energy consumption. So I'll talk about this a little bit later. So after this profiling, code from multiple applications is merged, visualized, compiled, and linked. And then finally, the firmware image is installed on the Amulet device. So let's talk about the Amulet Resource Profiler, or ARP, and why this is a necessary part of the platform. So you can put a lot of effort and time into making a really low power piece of hardware. You can co-design to your heart's content with the operating system, optimizing your drivers and peripherals to save energy. However, none of this will get you anything if a developer chooses to write an inefficient app on the platform. For example, if a developer sampled the gyroscope at just full speed and did single byte unbuffered writes to the SD card, the device lifetime is really going to suffer a lot. So the number one concern of users, as I've mentioned, for today's smartwatches and phones is the battery lifetime. The number one concern of the developers is to make a working app before the deadline. Like, these priorities are a little misaligned. So our thesis is that if you give developers constant feedback about where their energy is going as they are writing their application, then you can get them to care enough to write better, more energy efficient programs, taking advantage of the low power features of the platform. So to make this possible, we need to construct an energy model of the hardware, investigate the code that is being called by the developer in their app, and then build an application energy model which can be worked by the developer to explore their app through an energy lens. So the first part of this process is generating a device profile. So this is information specific to the hardware, but agnostic of any application. It is similar to the device information already supplied by the Android device manufacturers to developers, if you're familiar with Android development. So the device profile lists things like the steady state draw of each sensor and peripheral, the sleep and active currents of the processor, the cost of specific API calls, especially ones that require a lot of energy. So this profile is gathered by a custom printed circuit board that attaches to our Amulet prototype and coordinates with an automatically generated Amulet application that exhaustively tests every API call. So this only needs to be run once for each Amulet device, well, device type. So anyone that uses this specific model of the Amulet prototype does not have to go through the process, as we've already done this for you. So the Amulet Resource Profiler can use this device profile to find where energy is going in an app. So the ARP looks at each state and transition, counts API calls and lines of code, and sums the energy cost of each state and transition. So the ARP constructs a parameterized model of the total energy cost for the app, taking into account the base draw, energy draw, and the sensor subscriptions. So we can derive the total energy cost of an app if we know how often a transition will occur. So some transitions we know will fire a certain number of times because they were explicitly defined in the programmer's code, for instance, a timer. Others are dependent on the environment, the user's actions, or the programmer's actions, which is outside of the operating system control. So these are unknowns. So for these events, we have to take programmer input to fill out the model, allowing us to predict the energy cost of an application, and from that, get an estimated battery lifetime. So an interactive version of these results is presented to the application developer as they write their code. So we call this ARP-View. ARP-View lets the developer explore their application's usage of energy and see what happens when transitions or events are triggered at different quantities for some time period. So either days, hours, or minutes. This UI lets developers explore the energy trade-offs for different design decisions. So this is ARP-View. So ARP-View presents the application state machine. Transitions are annotated with the estimated cost of execution, as well as the number of times that transition is executed. The predicted lifetime is shown at the bottom, giving a breakdown of each of the application's contribution, as well as the total device lifetime with other applications included. So the sliders on the right-hand side let the developer fiddle with how their code behaves depending on the frequency of different events. So every time a slider is moved, the lifetime is recalculated and shown. So the developer has the best insight for figuring out how many times events will be fired because they know their application model better than we do. So we have to put that on the developer themselves. So this UI is updated every time the developer saves their code. So the developer could have code in one window and then ARP-View it in another. And so then they can explore the energy trade-offs as they create their app. So instead of doing this analysis at the end of the development cycle, as is typical now, when it's already too late. So we're really advocating for an energy-first approach to wearable app development. Since users' number one concern is battery life, with the Amulet Resource Profiler and ARP-View, it makes it much easier for developers to focus on energy as well. So I'll show a few results from our evaluation, including some studies we conducted with Amulet on users and on developers themselves. So for more information about the details of the evaluation, please check out our paper. It has a lot more interesting tidbits. So our first step in evaluating the platform was building 9 applications. 6 of them are shown here on screen. These applications included everything from a simple clock to heart rate monitoring that connected with Bluetooth Low Energy to an external heart rate sensor, and as well as survey delivery for smoking cessation, which was used by the Dartmouth College Geisel School of Medicine, one of our collaborators. So we measured the average power draw for each app on the prototype, and from this estimated the expected lifetime, accounting for battery wear with the 110 milliamp hour battery included in our Amulet device. So our lifetimes range from almost 8 months to 2 weeks with apps that do heavy logging and Bluetooth Low Energy communication. So we also wanted to evaluate how accurate our predictions were for each application using the Amulet Resource Profiler and ARP-View. For this, we compared the ARP battery impact predictions for each app with the actual battery impact computed from the measured average power draw, automating app transitions to match our model's input. So our prediction accuracy landed at 90% to 98%, depending on what the app or set of apps did and how well we profiled certain subsystems like the SD card. We also explored the usability and benefit of the programmers to the programmer when using ARP-View. So we recruited 10 computing students who all had some experience with low-power embedded systems. The students performed a set of tasks centered around app energy with ARP-View, and then were surveyed after this. So we found that ARP-View was generally easy to use, except for one person, for some reason. It encouraged developers to think energy first and made decision-making about energy-efficient application code much easier. So we also did a pilot study on smoking cessation in partnership with our colleagues at the Geisel School of Medicine at Dartmouth. So we deployed amulets on 6 participants over the course of a week, gathered over 70,000 heart rate readings, delivered smoking cessation surveys, and recorded about 48 hours of use. So the participants also answered usability questions, which actually informed our latest case designs, where we added flexible buttons and made the form factor smaller and added rounded corners, because that's the big thing now. So this really successfully demonstrated the feasibility of deploying mobile health applications with medical practitioners, non-technical medical practitioners. So overall, our evaluation tells us that with Amulet, developers can create interesting applications with energy-focused, helpful tools on a usable hardware device that has incredibly long battery lifetime and is useful for a variety of studies in mobile health and other areas. So there's a lot we could do in the future with this. We're looking at secure firmware tool chains from developer upload to an app store to installation on the device itself over the air through the phone. We're investigating better networking abilities to enable the body area health network. We're also, most exciting for me is with the low power abilities of the platform, energy harvesting to achieve energy neutral or even opportunistic execution now becomes possible. So you can imagine attaching a small solar panel behind the screen of the Amulet, trickle charging a capacitor or a battery, and negating the need to ever plug your device in. So, but most importantly, really, we are doing all we can to enable researchers, like everyone here, to do cool things. So we have ongoing projects with researchers at Dartmouth, Clemson, and WPI investigating smoking cessation, exercise recognition for the elderly, stress management and detection, sleep monitoring, and many others. So to summarize, Amulet is an open hardware, open source wearable platform that we envision enabling a host of really cool long-term applications in mobile health and elsewhere. So I invite everyone to go to the links shown on screen, download Amulet, check it out, learn more by visiting our website, and taking a look at the code and hardware designs. Thank you very much for your time.
All right. Hi, Kent Lyons, Technicolor. I wonder if you could comment a little bit on basically the errors in your predictions for the battery life. Is this your profiling wrong? Is this the user guessing the wrong parameters, or is there something else going on?
So, yeah, you kind of touched on some of the places where the errors are. So we generate this device profile, and if we happen to, the accuracy of the device profile depends on the accuracy of our measurement system. So minor errors can compound in that, which can reduce our accuracy. Also, certain hardware components like the screen or the SD card, depending on the input, the data to the that uses the SD card, can change the actual amount of draw. So you'll probably draw more if you write a 100-character string than a 1-character string. So to get around that, we did try different levels and different parameters and use that to inform how we profiled our API calls. But yeah, there is still a source of error, and we're still looking at ways to improve that.
Okay, any other question? If there's no more question, let's thank speaker again.